and welcome to another episode on the White Dog Garage YouTube channel. My name is Bob. In this episode I'm going to be making a pair of roller stands. These are used to check the run out on shafts and also to balance things like grinding wheels. I have brought in 4 sets of bearings to make the roller stands with. The bearings I'm using for this set of roller stands are NSK 6405ZZC3. Obviously 2 roller stands and 2 sets of bearings per roller stand. They are a deep groove ball bearing metal shielded set with an internal diameter of 25mm, an external diameter of 80mm and a width of 21mm. The way it normally works is you set up your bearings in the stand in a position like this. The roller stands I'm making here will be able to hold shafts up to about 75mm or about 3 inches and down to about 6mm or about 1/4 of an inch in diameter. Now you can use smaller bearings, and really the bearing size and the bearing separation determines the size of the shaft that you can deal with. So if you were dealing with, say, bigger shafts, maybe 150mm in diameter, then you might move your bearings out to this position or thereabouts so that the bigger shaft can run between them. If you're dealing with very small shafts, then the closer they are the better, and these are probably, as I say, I'll be running down to about 6mm. If you're making a set of roller stands, you can use smaller bearings. The separation distance and bearing diameter determines the size of the shaft that can rotate on the stands. The important things with a roller stand are that the bearings run true and do not contribute any play to the shaft rotating on them. The bearing holes are 25mm or just under an inch in diameter. I could use 25mm diameter bolts to hold them, but I will instead use 12mm diameter bolts and use the lathe to make hubs to hold them in place. Roller stands are a relatively simple build. You need to set up a framework to hold your 2 bearings and to have a base, a reasonable base in which they set. The important thing is that the bearings be at the same height. In the 2 roller stands, the 4 bearings all need to be sitting at the same height. That is probably the only critical measurement apart from fitting the bearings. I start by cutting out the material I will use to make the roller stand frame. 4 pieces of 100 by 8mm mild steel bar, 190mm long, will form the uprights, and 2 pieces of 50 by 6mm mild steel bar, 200mm long, will form the base plates. All the uprights need to match, so the next step is to stack weld them. That is, the 4 plates are aligned against their rolled edge and the cut ends tack welded together. Next, I mark up the plate stack for drilling the 2 12mm diameter holes for the bolts to hold the bearings, as well as a central 30mm diameter hole which will form part of the central shaft gap between the bearings. I use the bench drill to make the 2 12mm diameter holes. I start by drilling a 6.5mm pilot hole and then swap out to the 12mm drill. Relocating the plate stack to the milling machine, I use a 30mm annular cutter to drill out the central hole, which will be the start of the shaft gap between the bearings. The only problem with using the annular cutter is that I need to remove each disc as the cutter goes down through the successive plates in the stack. We've now drilled our 30mm hole in the stack of plates. You could just as easily run a V down to that depth. At the end of the day, you are essentially just providing a depth down between the two bearings for a shaft to run. What I'm going to do now is just curve down the edges, cut down from the top, and just provide a gentle curve. Just a hint here, the flat part of the grinding wheel will give you a reasonably square surface. So when I've been grinding here, I have been using this part of the grinding wheel rather than the nose, because I've got the 4 plates to go down through and I want them all to be equal. Back from a bit of filing, it's all neatly ready to go, and we are now at the stage where we can grind these welds off and split the plates. I was merely going to grind off the welds, and then I had a closer look at it. I've got some plates that are not quite the right distance there. This is squared up here because that's the corner I squared on. And then when I look at the distances to the centre holes, that was also different. I'm going to cut those edges off. The trick is, what do I cut them off with? I could use the coal saw. It'll work well on the wider one. Won't work so well on the very narrow one, because you've got that chance of the blade flexing. But what I'm going to do is just quickly put it in the mill and just mill off both ends. Now the other thing you'll probably notice is I've bolted it together, and that's because once the welds are broken, the plates will come apart and the whole thing will move. So to stop that, I've put bolts through both the holes that I pre-drilled, and that will hold it together when the welds are broken. In the end, I took the whatever works easiest approach to this, squaring up the uneven end in the Hafco HM45 milling machine using a 20mm end mill mounted in an ER32 chuck. I then used the horizontal bandsaw, another Hafco product, to cut off the excess on the other end. Okay, we've got the plate stack done, but this here is the first of 8 hubs that I will be machining up to hold the bearings between the plates. It's a sliding fit into the bearing, it just sits like that, rolls in like so, and there'll be one on the other side. It will grab the centre of the bearing, holding it in place, allowing the outer to spin. Not a terribly difficult machining exercise. It's done on the lathe, but I am starting with 50mm diameter hot rolled. And it's awful stuff to machine, as anybody who's done a bit will tell you. But it does work. What I'm going to do is machine it down to approximately 40mm in diameter, which is the large diameter here. Then I'm just going to cut, and this is the first one, and I'll cut 7 more about 25mm long. The dimensions of the bearing hubs are shown here. The major diameter is 40mm and its width is 10mm. The width measurement needs to be the same for all 8 hubs, as that width for the 2 hubs together with the bearing width determines the separation distance of the side plates of the stand. But also, the design is that the hubs grab the inner race of the bearing. Uneven widths would allow a hub to rotate with the bearing, which is not what is wanted. The minor diameter is 25 millimeters and it's machined to provide a sliding fit within the bearing. And I'll talk more about how to achieve that later. The width for this diameter is 10 millimeters again. Can be slightly less than 10 millimeters, but it can be no more than 10 millimeters. This diagram shows the two hubs in position on the bearing. That's the bearing there, and that's the two hubs shown in blue. The width of the bearing is 21 millimeters, hence keeping the width of the minor diameter at 10 millimeters or less ensures at least a 1 millimeter gap between the hubs. This is important to ensure that the inner race of the bearing is clamped between the two hubs. The hub blanks have already been machined down to a diameter of 40 millimeters, so I start by mounting it in the lathe chuck and facing off one end. I then proceed to machine the minor diameter down to a length of up to 10 millimeters and a snug fit on the bearing's inner diameter. I am machining the hub to have what is called a locational or clearance fit when sliding into the bearing centre. This type of fit is used to provide a snug fit on stationary parts. The hub's function is to grip the inner race of the bearing, holding it and not allowing it to turn. But if needed, the bearing can still be removed, so the shoulders of the hub trap and hold the bearing centre, but the hub's shaft must be a snug or sliding fit. These bearings should never wear out in practice, but living close to the coast in the northern half of Australia, rust is my eternal enemy. So they do need to be able to be removed from the stand and replaced if needed. I do not want to turn this video into a lecture on shaft fitting, but a recent question from a viewer on one of my other videos asked about interference fits. This alerted me to the need to explain the process a bit more. That viewer was looking to me to give a clearance value for a part, which he'd not told me the dimensions, that he wanted to machine a sleeve for. I suspect he wanted as a response a rule of thumb or something like make the shaft 0.02 of an inch bigger than the hole he was forcing it into. It is not that simple, of course. Clearance values depend on the diameter of the shaft. There are American National Standards Institute, acronym ANSI, and International Organisation for Standardisation, acronym ISO, standards for this. Their recommendations are captured in published charts covering loosely clearance, transition and interference fits between shafts and holes. These are reproduced online. Search for something like interference fit and in reference books like the Machinery's Handbook in the USA and the Engineer's Black Book here in Australia. In short, the clearance value depends on the respective diameters of the shaft and the hole into which it is being inserted, as well as the type of fit. The AL336 is an imperial lathe, so I'm going with inches in my example and using the ANSI standard as my guide. The ISO standard gives essentially the same result in millimeters, so use that if you have a metric lathe. The bearings I'm using have an internal diameter of 25 millimeters or a fraction under 1 inch. This chart shows the ANSI locational clearance fits for a range of shaft or hole diameters. I'm going with the class LC2, which is what is used to give a snug fit for stationary parts. My hole diameter lies between 0.71 and 1.19 inches. Our hole, H7, can be as much as 0.8 thou oversize, and our shaft, H6, as much as 0.5 thou undersize. This gives a minimum clearance of 0.000 of an inch, or 0 millimeters if that's your style, and a maximum clearance of 1.3 thousandths of an inch, or about 0.033 millimeters. The bearings I'm using are NSK 6405. Their internal diameter is 25 millimeters with a tolerance of 0 to -10 micrometers. That is, the diameter can be between 24.99 and 25.00 millimeters, or spot on at 25 millimeters or 0.4 thousandths of an inch undersize. How is this working in practice on the AL336? I start by machining my shaft to a diameter of 25 millimeters. I then check with a bearing, which usually doesn't slide on, but could if I use pressure, if I hit it with a block of wood and a hammer. I then reduce the diameter by 0.5 thousandths of an inch and check my bearing fit. If it is close but still not sliding on, I then reduce the diameter by a further 0.5 thousandths of an inch and check my bearing fit. And if it fits snugly, that's it. Otherwise, I guess I'd continue the process. 0.5 thousandths of an inch is a very small amount. My approach here is to creep up on that fit with the lathe rather than trust my fate to a micrometer. With the minor diameter machined to a sliding fit on the bearings in a race, I reverse the blank in the chuck, face off the major diameter to a width of 10 millimeters, and with that done, I drill the 12 millimeter center hole and the hub is finished. On to the next one. With all the hubs machined, it's time to split the plate stack. I then do a quick clean up of the plate edges with the flap disc. I still need to weld the roller stand frames to their respective base plates. The easy way to ensure frame alignment is correct is to first assemble the bearings and hubs within the plates. Turning the frame sets over, I then fixture the base plates in position on the upside down assemblies. Before tacking the base plates to the frame assembly, I have sprayed it liberally with anti-spatter and wrapped the bearing area in an old woolen blanket. Just a hint here, old or thrift shop sourced woolen blankets make for a cheap and effective welding blanket. With the roller stand frame tacked up, I then removed the bearings and the hubs and welded the frame out. If you're interested, the electrodes are 3.2mm or 1/8 of an inch E7016 and I'm running them at 120 amps. Back from paint, the completed frames are refitted with bearings and hubs and they are ready for use. Roller stands have a variety of uses. Here I'm checking the run out of an old tube that I want to recycle. Roller stands can be used for balancing wheels, for example bench grinder wheels, or as a support for a shaft rotating in the lathe. There are many uses for them. Thanks for watching, and I hope you found this video interesting. You may even want to make your own roller stands, in which case I hope this video has given you enough information to help you design and make yours. Once again, thanks for watching, and I hope to see you at another video from the White Dog Garage YouTube channel. Bye!